Printed paragraph problem. And a student types a paragraph on her word processor. Then she adjusts the width of the paragraph by changing the margins. Figure 8-3J, and the table shows the widths and number of lines the paragraph takes. So this is the table of an A, arranging the margins and the number of lines called Y that fit the paragraph, okay, with respect to the inches of the width or the marginal, the margin itself, okay. So when the margin is 6.5 inches wide, then the number of the lines that would fit the paragraph would take only 5 lines. Wow, that's so, so few. Okay, if the inches or the marginal inches is 5.5, then the number of lines would be 6. If it's 5, then the number of lines of the paragraph would now be 7. So if he lessens the margin, okay, and finally going down to 1.0, then she noticed that the number of lines that would fit the paragraph would be 38. Okay, and so she, let's say, she graphed it. This is the width of the margin, and this is the number of lines, or the Y. Okay, and when she plot the points on a graph, okay, she got this scatter plot. Okay, so letter A, would it be possible to make the width equal 0? And why? Then would the decreasing power function be more reasonable than an exponential function for number of lines as a function of paragraph width? Confirm that the power function fits better by running both power and exponential regressions and comparing the correlation coefficients. So this is the answer. When we first we are going to answer, would it be possible to make the width equals to 0? Yes, it is possible, right? By using margins as width, total the page width. So if we're going to use margins, which is whose width total the page width, so meaning we don't have any margin at all. Okay? Now in that case, the paragraph would be infinitely long. As in, in the notepad, sometimes you take note that when you don't have any margin there, it just runs. The lines just runs. So the paragraph would be infinitely long, matching a decreasing power function rather than finitely long, such as a decreasing exponential function would suggest. Now you can see that when we decrease the margin, okay, the number of lines increases, right? So looking at this suggests that it could either be an exponential function or a power function. But since we have justified that a power function could fit this because the width could be equal to 0 when we adjust the total page width to the margins. Well, there's no margin anymore, I mean. Okay, so we could use the power function actually, then an increasing or a decreasing exponential function. So anyway, running the regression for both the power function and the exponential function in your grapher, we will get y is equal to 37.2746 x raised to negative 1.0697 for the power function. And look at the correlation coefficient. The correlation coefficient is negative 0.9992. While taking a look at the exponential regression will give us y hat is equal to 41.1776 times 0.7025 raised to x, which is increasing, okay? Then, or it's increasing. Yes, why? Because we have less than 1 here, in between 0 and 1. So it is decreasing. But we have r is equal to negative 0.9674. So as you can see, the correlation coefficient of the power function is much greater than the correlation coefficient of the exponential function. Therefore, the power function fits perfectly the regression function for this scattered data. Letter B, plot the power function and the exponential function from part A on the same screen as the scatter plot of the data. How does the result confirm that the power function fits better? So this is the sketch of the both regression. We have the power function, so it's a solid line, okay? This line, and we have the did I say power function? Yes, okay. The exponential function is the broken line, okay? Now note that for the power function, you can see that the data or the points fit perfectly well, but almost perfectly well, okay? But for the exponential function, look that it misses some of the points. It just it crosses this point and these points in particular, but misses some of the points, like they have some residuals here, here, and here. Okay, so this only explains that the power function fits better than the exponential function. Letter C, because each paragraph contains the same words, you might expect the area of the page taken by the paragraph to be constant. In a list on your grapher, calculate the area of each paragraph. Use the fact that there are 7 lines per inch. Okay? Make a scatter plot of the area as a function of paragraph width. So the width of the paragraph. Okay? Bilinear regression show that there is a downward trend in the areas, but that the correlation is not very strong, and sketch the graphs and points. So these are the sketch, and these are the scatter plot, and these are data. So the area is, what is the area? X times y over 7. Area is supposed to be x over y, but since the y is, there are 7 lines per inch, so we have to divide this by 7, right? Okay? So these are, what do you call this, data representing the area of, what do you call this, of the page taken by the paragraph. So if your paragraph has 5, for x, for example, you have 6.5, right? So the width is 6.5, and you only have 5 paragraphs, or five lines for each paragraph. So the area is 4.6428, right? And then you decrease the width, make it 5.5, and you got 6 lines for the paragraphs, and then your area is 4.7142. Okay, and then you decrease it again. You decrease it again to 5 inch. The width becomes 5 inches. So your y accommodated is 7 lines. Okay, the area is 5. Okay, we're using this formula. Okay, And if it's 3.75, then the y is 9 and the area is 4.8214. And finally, when the area is reduced to, or when the width is reduced to 1, the number of lines is 38 and the area is 5.4285. Right? Now we could use a linear regression for this. And the linear regression produced by your graphics calculator is negative 0.1090 x plus 5.3325 with a coefficient of correlation which is negative 0.7883, which is weak correlation. So when we sketch the graphs and the points, you can see that your line misses some of the points also, and it only has these 2 points as fitting perfectly on the line. So therefore, when we have a linear regression, well, the downward trend in the areas have such correlation, but they are not very strong. There is a downward trend, but you could see that the correlation is not very strong, right? Okay, so that's the answer for letter C.